So I will just quickly introduce ourselves and we shall begin.
Wonderful. Yeah. I see people still joining though. If we want to give them just a few minutes.
I'll do it
See a bunch
slowly.
of people. All right. Sounds good.
Okay, so just a few words about what Vericube is. My name is Gregory. Vericube is doing engineering services, mainly in industrial automation and product design, helping companies go from idea to working hardware and production. In addition, we are Canadian representatives for a few great partners: Frenetic AI for magnetic design and simulation, Acrobis for direct drive motion systems, and IDS for industrial cameras. Well, I think this is it, and I think let's get going. We'll start with some easy questions, and hopefully more people will join as we go.
Yeah, so, happy to give a little introduction about myself. Hi everybody. Yep. My name's Danny. I run Sunburn Schematics. We are a company dedicated to power conversion in space. And what we do is build high power density DC to DC converters that are radiation tolerant and survive the various environmental challenges in space. And moreover, we do so for the new space industry. So we have a unique approach to designing DC to DC converters that's different than what traditional aerospace and space clients have designed themselves and have requested.
Well, this is awesome. Danny, how did you end up doing electronics for space?
Well, it's actually funny. The other day, Facebook showed, like 10 years ago photo, and it was a photo of me holding up a three-phase H-bridge from one of my first ever projects. And when I was a physics student in my undergrad, I got involved in building electric skateboards, and I decided I wanted to build one from scratch. And so I started learning power engineering in my spare time. And eventually, through a series of other academic steps, as well as let's call it jobs, I've sort of found myself as a power engineer. I got another undergraduate in electrical engineering, and my first few years in industry, I worked as a robotics engineer, and I was always kind of working on these challenges where it's like high electrical power density combined with like a thermal challenge. So like high power lighting systems, various power distribution boards, controllers for motors, things like that. Places where you've got a lot of electrical power and you have a lot of thermal considerations, and that's kind of naturally grown my skills as a power engineer. And eventually, I decided to start my own company.
Well, this is great. So, Danny, you mentioned now and when we spoke before that the industry is divided for, let's say, new space and the old space. Can you tell me more about it?
Yeah, so the reason I got very excited about space, and by the way, I don't have a space background. I wasn't an aerospace engineer, nor have I ever worked at a traditional aerospace company. But I decided to move from the agricultural robotics sector over to aerospace specifically because of this transition that I saw from the new space from the old space paradigm to the new space paradigm. And what that paradigm shift looks like is very similar to early days automotive industry, where you had these behemoth Fords and Chryslers and things like that who would build, design, and manufacture everything vertically integrated in-house. And eventually you had this kind of commodification period where you went from kind of bespoke internal engineering to a very diverse supply chain of various subcontracting, sub-manufacturers, contract manufacturing firms, and various sub-suppliers for various parts and goods that would go into a car. And I'm seeing the same thing happen in aerospace. And as somebody who's pretty passionate about manufacturing and supply chain as well as power engineering, I wanted to play a role in that. And I see many slots open for folks to provide various subsystems at scale for the new space industry.
So let's talk a little bit about what that actually means to make power electronics for space. What are the differences between what you do and what we could do for, well, terrestrial applications?
So a lot of it's similar, right? It's, at the end of the day, the topologies are pretty much the same. There's many of the same thermal challenges, sometimes vibration challenges, especially as your satellite's going into space. What the biggest difference is is radiation. And there's not a lot of places on Earth where you're designing for high radiation loads, with the exception of maybe power converters that are used in nuclear facilities, on accelerators, and sometimes in commercial aircraft. Does that answer the question? I think.
Yeah, it does. So how do you select your components for what you do?
Yeah, so for us specifically, because we're targeting a new space paradigm where folks are launching much more rapidly, they're launching for shorter duration missions, and they're launching more frequently. So not only are the design schedules much shorter, but the actual launch cycles are of high frequency, and the companies don't expect their satellites to last 10, 20 years. They're only looking for missions that are kind of 3 to maybe 7 years in low Earth orbit. So what that means is we're able to use automotive grade components. So instead of targeting specifically radiation tolerant by design components that are thousands of dollars each sometimes, we are using simple off the shelf automotive components that are like we're designing a 500-watt brick right now for powering server infrastructure in space, and the most expensive component I think is $19, and that's like a power controller chip. But the way we've selected that chip is that we work with radiation consultants who have a good understanding of what could pass radiation, what could survive in various radiation environments. And then we'll take those components, we'll create coupon boards, and we'll actually book slots at linear or cyclotrons, like particle accelerators. We'll blast those components with radiation, and we'll see what sort of damage they sustain and what sort of fault behaviors they have. And I could get into that a little bit on what types of radiation damage there are in space. So roughly speaking, there's 3 types of damage that people consider when building for space. The first one is, and I'm sure you've all heard of this, bit flipping, right? You have a high energy particle or something hits, it deposits some charge onto a CMOS gate, for example, and one of your bits in memory flip. That's actually the easiest one to deal with, and oftentimes, you just reset your chip, or you have redundant memory, things like that. The second type is destructive events due to high energy particles. So something like a coronal mass ejection or a galactic cosmic ray, those might be particles, in the hundreds of mega electron volts. That'd be the equivalent of, tossing a softball at somebody, but in a single high energy proton, or a single high energy atom, basically, that slams into your electronics. And what that can do is actually punch holes through semiconductors. It can severely disrupt various parts of the circuit, and so those are really hard to build around. And typically, the way that you protect from that is you have chips that are resilient towards high energy particles. So they just, however they're constructed, they're not as damaged by these high energy impacts. And you can mitigate it through architectural decisions. So parallelizing like MOSFETs, for example, or things like that. And then the third type of damage, that you see most often in space is just general degradation due to ionizing radiation. So as these high energy particles come your way, and sometimes lower energy particles, maybe ones that are, single mega electron volts or maybe tens of mega electron volts, they're not high enough energy to really damage your chip outright. They're not going to punch holes through it. But what they are going to do is they're going to displace, atoms. They're going to break apart your PN junctions, and maybe you'll have, a charge migration. And what the effects of that are is you'll have like increased leakage current, for example, in your semiconductors, or maybe your gate thresholds change. And at some point, they might drift far enough such that the functionality of your device is impaired. So maybe you've got like a voltage reference, and over time, that voltage reference shifts because of this sustained low-ish energy damage. Yeah.
Okay, so do you use any kind of protection for the electronic devices?
Yeah, so protecting from radiation is kind of a double-edged sword. So if you put, for example, aluminum between your semiconductor and a radiation source, such as the sun, you'll protect against these low-energy particles, and so you're much less likely to degrade, to have like the type of degradation I was just talking about in your device. But on the other hand, if you have a high enough energy particle and it slams into your protective aluminum shielding, what it can do is actually create a shotgun burst of other high energy particles that now pepper your entire circuit. And so what ends up happening is folks that fly electronics in space, they'll use the orientation of their electronics towards the sun to mitigate some of the damage. So imagine we've got the sun over here and your spacecraft is flying here. If you position your electronics such that it is facing the sun directly, you will have a bunch more surface area where these high energy particles can interact with your semiconductor. But if you fly orthogonally to the sun, you'll actually have less surface area where these charged particles can interact. But now you have this issue of the shotgun effect. You have a single high energy particle that might pierce your entire silicon lattice. And so what people end up doing is they'll fly it with a slight inclination towards the sun, roughly 30 degrees or so. And that provides the most amount of kind of shielding to your devices. But they'll put some aluminum, and there's kind of there's an optimal thickness for a particular orbit, for a particular mission duration. And folks who are more experts in the radiation side of things typically decide those things.
Okay, let's talk a little bit about the design itself. So what are the common topologies that you use for power electronics in space?
Yeah, we've designed forward converters. We've designed push-pull converters. We would love to, as we get into higher powers, we'd love to switch over to dual active bridge and other more modern topologies, LLC type converters. But realistically, what we're competing with is old school topologies that are 80, 85, maybe 90% efficient with very low power densities. And the real challenge for a lot of space folks is finding power converters that use more modern technologies that are actually radiation tolerant. And so one of our main competitors, VPT, they have a whole plethora of various power converters that you can buy off the shelf, put on your satellite, fly, and they'll work. But you're looking at 50 watts per cubic inch of power density, roughly, I don't know, 0.2 to 0.5 watts per gram weight, power to weight density. We're targeting 3 to 5 watts per gram, and the previous power converter that we delivered, we hit almost 400 watts per cubic inch on a 1 by 1 inch 100 watt power converter, right? Exceeding some of the specifications of like the most cutting edge Vicor products for automotive. And so we're able to use these newer technologies, build them to be radiation tolerant, but not radiation hard, right? With an expected mission duration of roughly 3 to 5 years, and actually have things that are comparable to what the automotive or maybe military uses in terms of like power density, but actually bring it to space clients.
Tell us a little bit about the thermal challenges and solutions that you have.
Yeah, so thermal is a pretty big problem in space. As I'm sure you guys have heard, there's this wave of like, oh, let's build data centers in space. And then there's a counter wave of like, oh, the thermal challenges are too hard. And what it turns out to be is that for every roughly square meter of solar panel, you need roughly 0.3 square meters of radiator. So if your sun's here and you're flying your satellite and your solar panels are perpendicular to the sun, what you'd want is radiators that are orthogonal and point towards cosmos, and they're radiating heat. The challenge there is you've got somewhere in between, you've got your compute unit or some other satellite that's very power dense, tens, maybe 20, tens, maybe hundreds soon of kilowatts. And you've got to take all of this electrical energy, do something useful with it, convert it to heat, and then expel it. And so the pressure on satellite builders are twofold. A, they need to figure out how to take all this waste heat, and remove it from their core satellites into their radiators. And the other one is, how do you produce less heat? And that's kind of where we come in, right? Current architectures, current products on the market, they're quite low efficiency. Right? I was saying 80, 85, 90% efficiency. So the question is like, can we push that to 95, 96, 97, 98, right? And produce a hell of a lot more heat and simplify the challenge for the developers of these high power density satellites. And in space, the only thing you can really do is conduction, right, within your spacecraft. So for our power converter, we need to be, conducting from our case, from the, from our power converter to the chassis of the satellite, and then the producer of that satellite, rocket, or other vehicle needs to then re-radiate it back to space. And I have a non-encapsulated prototype here of 100 watt, this is a 500 watt power converter. And once it's encapsulated, it's essentially just a black box that has high thermal conductivity, and it's mated directly to the aluminum chassis of the satellite. And so we extract the heat from the circuit through conduction, and then later it is extracted through radiation on the radiators of the satellite or other vehicle.
Okay, so I just want to take a minute and ask all the visitors, please ask your questions. We're going to do some Q&A in a little bit. And for now, Danny, how do you actually test the thermal aspects of your devices with no air? Do you have a vacuum chamber in your lab?
Yeah, so I have a TVAC. I have a small TVAC chamber. It's not rated quite for the temperatures that we need to test out, but it can get me some preliminary results. And then the customers who I work with, pretty much every, even small space company has their own thermal vacuum chambers where they can cycle and do the type of repeated thermal stress testing, as well as a conductive thermal testing in a vacuum. And so a lot of our testing is done through our customers. We both for the radiation testing, right? The slots at the linear cyclotrons at the particle accelerators, right? We get those slots a lot of the time through our customers. They'll be testing some of their equipment. They'll be like, hey, we have like an extra hour or two free, and so we'll fly out and we'll go test the chips that we're building for them together with their team. Same thing for TVAC. We recently, a customer, pre-ordered some engineering modules of the 500 watt power converter that we're currently working on. They're like, hey, we have a TVAC chamber and we'd love to test to this particular, thermal profile, right? And it's different than what the original customer who purchased this engineering work from us needed. And so we'll work with these guys to see if our devices also pass this new thermal profile. And if they do, great, they can use our chips directly and go solder them onto their boards and fly them. And if not, we might be able to come to an agreement to re-engineer our existing devices slightly so that it meets their thermal needs as well.
So speaking of testing, how do you test for radiation?
Yeah, so radiation, maybe I didn't grab any coupon boards. I don't have anything for show and tell, but essentially, you create a setup where, let's say you've got some switching components or some MOSFETs or something that you're not sure whether or not they will withstand radiation. You'll put them on a big coupon board, subject them to the expected electrical currents and other kind of inputs, and then place them in front of a particle beam, and you bombard them with heavy ions or protons or whatever you're testing for, and then you'll have like oscilloscopes or a big test setup where you're collecting information from that, and you actually see how do they behave when they're impacted by heavy ions or protons or whatever it is that you're testing for. And you gather that information. Based on that, you make an educated kind of guess as to how to build your entire device. And then once you've built your entire architecture out of chips that individually have passed radiation, then you go and you retest it. And so you put it in front of the particle beam, and you know, if you did your job well, then the entire component, the entire set of components also performs as expected together.
Does the beam represent the actual radiation level?
No, so it's accelerated, both when you're testing for total ionizing dose, which is the slow degradation due to ions, as well as when you're testing for heavy ions, which is your high energy particles. Those are both accelerated tests. You're seeing, you know, hundreds of thousands, if not millions of times more particles during test time than you are in space. Moreover, you're seeing so many particles that, you know, when we're doing our last test and we had some thermal cameras like pointed at our circuit boards, you can actually see the material in front of the beam heat up just from impacts of individual like particles. And so you work your way back, you know, let's say you see every 5 seconds you see an error. You calculate how many particles per second were hitting your board, how big were your chips, how many of those particles were hitting sensitive areas in your chip, and you kind of work your way back and figure out that how often you are expected to see those same errors at the orbit and inclination that your satellite or rocket will eventually be flying.
Okay, so I'll start asking some questions from our folks, our viewers. So what voltage value we need to power up all the modules?
Yeah, so in space, there's a few kind of voltages that folks target. So your ISS, your larger satellites, they typically have a roughly 100 volt main bus. So your solar panels will be somewhere in the 80 to 140 volt range. And so your bus will be somewhere around there. That usually gets down converted to 28 volts, 12 volts, 5 volts, and 3.3 volts. Your isolated voltage conversions are typically between your roughly 100 volt bus and your either 48, 28, or 12 volt kind of lower subsystem. Typically, the way that a larger vehicle is constructed is you have various avionics boxes, and each one is powered from either 28 or 12 volts, and you'll feed a higher voltage to those boxes, and then you'll down convert at the point of load, or at the box, and then at the point of load, you'll have non-isolated converters that maybe take 12 volts down to 3.3 or 1.8 or whatever it is that you need on within your board. On a medium or small sized satellite, you'll oftentimes have roughly a 48 or 28 volt solar panels, which will feed into your battery system. Your battery system will be somewhere between 12 and 48 volts, and then that gets down converted. And sometimes those customers don't need isolated voltage. it depends on the topology of your spacecraft and how you've decided to do your power distribution.
How do you prepare the boards for the rocket launch in terms of vibration?
Somebody called my phone. I hijacked my connection. Give me just a second. Fix that. Sorry, say it again.
Yeah. So the question was, how do you prepare the boards for the rocket launch in terms of vibration?
Yeah, so a lot of the time, our customers
Danny, I can hear you.
All right, test. Okay, that works. All right. Sorry about that. My phone hijacked my Bluetooth connection. It's not letting go. So we'll do it this way.
That's okay.
Yeah, so thankfully the boards that we build are relatively small, and so we don't have huge vibration concerns. That said, we will still test that with our customers. So for example, our customer needs to do vibe before SpaceX will let them fly their satellite, and so once they solder our boards onto their main boards, they'll vibration test the entire thing in a vibration essentially stand, and then they'll know whether or not it passes. We work with the vibe teams within our customers' companies in order to design something that is most likely to pass vibration, and they typically have plenty of feedback on, like, okay, look, this mass is 100 grams. We need an M3 screw close to the center of mass so that we can bolt it to the chassis and not just have it soldered onto our main board. We need further vibration considerations, but typically the customers will, for us, we don't have a mechanical engineering team. I know how to use SolidWorks and I know how to tinker around with mechanical elements, but I'm not like a vibe guy. I'm not a mechanical engineer, and so I'll end up working with the folks there.
Where does the power come from in space?
Say that again. I just had to switch audio.
Where does the power come from in space?
I'm so sorry. Give me just a second. It's 21st century. I'm still having technical.
Well, it's live. That's a good excuse.
Okay, test.
Yes, we can hear you. Okay,
Oh,
so
man.
the question was, where does the power come from in space?
Okay, test.
I can hear you. Can you
Okay,
hear
perfect. Yeah, we're back.
me? Okay. And
yeah.
did you hear the question?
No, I did not.
The question was, where does the power come from in space?
Usually solar panels, unless you're a state actor, or I think there's some private Chinese companies that are putting RTGs, radiothermal generators, on board their spacecraft. There's
Small nukes.
there's proposals to do full nuclear reactors, but we're not really there yet. But it's usually solar to battery, from battery to whatever subsystems, or sometimes directly from solar to various high power systems. Actually, Volta Space, they're flying on a lunar mission soon, and what they're doing is laser beams. So they have an antenna that's able to capture laser energy at high efficiency. It's essentially a solar panel tuned to whatever the frequency of their lasers are, and then they're beaming it across the lunar surface or from satellite to satellite. There's also some microwave beaming companies that are exploring that, but I'm not super familiar with that type of power sending and deployment.
Okay, another one. You mentioned a couple of times that the life expectancy of the power converters is somewhere between 3 and 7 years long. Well, I guess not just power converters, the whole thing. How much longer do you think that will be the case? Or do you think the life cycle expectation will remain the same going forward?
I wouldn't be surprised if it actually becomes shorter. So my grandpa was the head of reliability for Roscom, which is Russian space agency, private. They did like geostationary satellites for like telecommunications. And when they were designing for 10, 15, 20-year missions, right? Because that's how long it would take for your return on investment to essentially, for your satellite to pay itself off, right? You need at least, 12 years or something to pay the satellite off, and only then are you making profit. But now that launch costs are so much lower, you're not worried about, having to pay off millions of dollars worth of launch fees. You can build a $250,000 satellite, launch it for, kind of high figure or high five-figure, low six-figure sums, and see recoup your investment in maybe a year, right? And so if you build a satellite that lasts 3 years, it's like, okay, you're spending a year recouping your investment, and then you've got like 2 years of profitability, right? That's kind of the type of dynamic that you're seeing now. And so as launch costs keep falling, as folks like us, provide cheaper and more accessible products, as companies are able to produce cheaper and cheaper satellites, you don't have to fly for as long, right? And so your engineering constraints kind of start decreasing accordingly.
So what kind of efficiency do you achieve with your models?
Yeah, so our previous are little brick, and I have them here for show and tell, non-encapsulated modules. So this one was about, I think it was 92% efficiency at full power. And this is a roughly 48 down to 28 volt converter. And there's one that also did 48 down to 12 volt conversion. This one was 92. The one we're building right now, the 500 watt one, is targeting 95% efficiency. But obviously, I'd love to build like dual active bridge LLC and kind of get into those 10 kilowatt range, and then we'll try to squeeze out even more efficiency. But this is where we are right now.
So I see a planar transformer on this device. What are the considerations to pick a planar transformer?
Yeah, so for us, size, it's almost entirely size and thermal. So planar transformers, it's really nice to suck heat out of them because you get a big, nice conductive surface where you can have it, kind of coming out of your encapsulation and directly in contact with whatever material or whatever the contact surface is that's pulling heat away. The second thing is, they're super compact, and if you design them well, you can get really low leakage inductance, and they're very manufacturable. So when I'm designing, I'm thinking immediately from the manufacturability perspective. All the designs that we make, our intended target volume is tens of thousands of units per year. And so when I'm designing this, I limit myself to like, what techniques can I use such that manufacturing at that scale is very doable at the cost targets that our customers are looking at. Price points per unit. Yeah. Mm-hmm.
I have a few more questions from the viewers. With high compute payloads, the transition from 28 or 100 volt bus to low voltage CPU GPU rails creates massive thermal bottlenecks, with a lot of core voltage being sub 1 volt. How do you manage the thermal challenge as well as aggressive transient requirements from on-off power cycles?
All right, so 2 questions. The transients and thermal. So typically customers will approach us to do the isolated stack. So taking your, let's say 100 volts, converting it down to 12, and then they'll have point of load converters that'll do 12 to 1 volt or whatever. But we've had folks approach us for, a 28 down to 1 volt power system, but non-isolated. And so you end up, if you're doing non-isolated, low voltage, you can do these, what are they called? Multi-phase, like buck converter topologies, where you can get super high efficiency and you interleave like a bunch of buck converters, and you do it right at the point of load, and you can get your 97, 98% efficiency. But that's not really what we do. We focus predominantly on the isolated part of this equation. So I don't know if that answers your question, but yeah, there's thermal issues. You got to suck the heat out. Good thermal design. Everything touches everything because you only have conduction, and so you need to have you have this whole thermal circuit essentially. That's your satellite. It's like, okay, you're like 3 layers inside your satellite, and you've got like, you're producing like 10 watts here. It's like, okay, how does that 10 watts going to travel through your entire satellite? And there's people who, thermal engineers dedicate their entire lives to getting really good at that question. For transients, well, yeah, soft start, soft stop, or are you talking about like transient, like load, like peak loads from your compute?
I think this is the intention.
Yeah, I don't really interface with that super low voltage stuff. I don't have a ton of experience there. Yeah, I would talk to folks who specifically work on that, like
it's the point of load converter that has to be extremely fast response, right? And then if voltage fluctuates on your high power device, then it's probably not such big of a deal.
Yeah, on us, we have a lot of bulk capacitance. There's a lot of inductance and like even just the cables that go to our device, right? We're not really seeing like megahertz blips in power. Things are the power coming in and going out. It changes slow enough where it's not really a huge issue.
So another question: what are the typical switching frequencies? What kind of microcontrollers are used for controlling the converters?
So switching frequency, the design, the little block that I showed you guys, that was a 330, I think, kilohertz. It was a forward topology. The one I'm working on now is 450 kilohertz push-pull. We're not using microcontrollers, and the reason is there's not a lot of microcontrollers that survive radiation, have the picosecond or nanosecond dead time insertion and high frequency PWM drives, and meet the cost targets that we need. And so we end up working with a lot of analog parts, with a lot of dedicated driver circuits and driver ICs. Now, that's not to say we don't have plans to test out a bunch of microcontrollers, and I have a whole list that I want to put them all on a single big coupon board, go shove them in front of the proton beam and see what happens. I'd love to be able to use some of these better microcontrollers, and there's definitely some that are available, but again, it's kind of this trade-off between complexity, power, cost. We're currently just using dedicated ICs.
Tell us about EMI in your devices. Is it a big concern? What do you do about it?
It depends on the customer, but for sure, you have to meet all the FCC regulations and everything. It depends on which customer, but some of our customers, they're like, hey, we have really stringent EMI requirements. And if they're going to purchase, our devices, they expect us to go and actually get all the EMI certifications and testing. One of our customers has a lab that they work with closely, and they made a pre-order on, again, engineering modules, and they're like, hey, we care about EMI a lot, and so we're going to have a test campaign. Part of our deal with them is like, okay, here's engineering modules. Let's go get them EMI tested to your specifications. And then if they pass, great. And if not, then we'll go and re-engineer them to actually meet the EMI requirements.
And are the specifications similar to what we see here on Earth, or?
Yeah. Okay, it depends. For commercial stuff, for commercial satellites, it's going to be basically the same thing. If you're trying to build for a NASA Ultra whatever, telescope.
The old space.
Yeah, for old space, they'll have some insane specifications that they're trying to meet that, like, I don't have the skills to, like, there's some gray beards out there that can do it, but that's not who we're targeting. These are kind of one-off, like, very bespoke, unique things that, like, real RF specialists, like, spend 2 years debugging and figuring out how to make them work, right? That's not really like, yeah. We're trying to meet like basic, automotive, the cell phone specs, that type of thing.
Okay, so a couple of more questions. You mentioned manufacturing. How do you plan on scaling to high volume production? When, and if it is the case of when, the demand for space electronics surges?
Okay, so there's a chicken and egg problem here for sure. And as a company that's entirely bootstrapped through NRE, right? Our customers come to us with like, hey, can you design this? We're like, yeah, and come up with, some amount of money to go do it. We don't have like cash lying around to like, oh, we have $1 million allocated to, doing a production run, like whatever, 100,000. And so we have kind of 2 or 3 paths. We can get a customer who's like, hey, I need 100 units. That'll be enough, or maybe 1,000 units, over the course of the year. And if they pay 30-50% up front, that'll be enough for us to go and actually do a manufacturing run with a contract manufacturer. Alternatively, we get enough customers who are interested in a particular unit that we can get, binding LOIs or the equivalent contracts that we can then take to the bank, get debt equity or basically debt-based financing, and go ahead and and fund this manufacturing run. The third one is go and raise venture capital. I don't know if you necessarily want to do that, but it is technically an avenue as well.
What software tools do you use on your design cycle?
Altium is number 1. Number 2, SolidWorks. LT Spice for simulation. It's pretty much it. I mean, some of the contractors and engineers I work with, they have their own preferred toolkits, but basically the designs are all in Altium, and then we'll do sim and various other things. I have Claude. I have an entire abstraction, hardware abstraction layer that Claude wrote for all of my like oscilloscopes and benchtop tools. So like for radiation testing, for example, it was all just Claude vibe coded over the course of like a week. So we can like interface with our tools, and I'm basically just using AI as a interface between myself and my testing equipment. So there's that. I hate LabVIEW, BenchView. What is it called? The old tool that allows you to like plot like oscilloscopes and stuff. It's LabVIEW, right?
It is, yes.
Yeah, I took one look at that in college, and I was like, it killed me.
Well,
so I've been writing my
own. Kind of relationship with LabVIEW,
it's just Python, right? I've been writing my own. Now that there's AI, it's just like, here, AI, go figure it out, and it works.
Okay. There's a question about switching elements. So judging by the frequency, are these GANs?
Yes, we use GAN devices. GANs, we actually use GAN devices not necessarily because they're super high frequency switching and super low RDS on or whatever. We actually use them because they're radiation tolerant. So GAN devices typically perform really well under heavy ion radiation, as opposed to like silicon carbide or regular MOSFETs, which they'll fail at like 10 or 20% VDS. Most GAN devices can easily survive past 50% VDS. And so if you're going to build around, a switch that can only survive at 10% VDS, you're going to be using like 1200 volts, silicon carbide MOSFETs for switching to 100 volts. And that's, or even 48 volts, right? And that's kind of ridiculous. But there's not a lot of GAN drivers that pass radiation. And so we have this challenge of like figuring out how to use old school silicon carbide drivers to drive GAN FETs at, the 3-4 nanosecond turn on time. That's a whole a box of frogs. I don't know, what do you call it? Like a can of worms. There you go. Yeah. And thankfully we figured out some good techniques that work.
Okay.
That's definitely a challenge.
I think it would be interesting to talk a little bit in general about the application trends in the space industry. Can you tell us more about it?
application trends.
Yep.
Okay.
Like,
Yeah. So, so space is, so the entire market of space, like right now, it's basically telecommunications. That's like, a huge aspect. Then there's a huge aspect of like launch vehicles. There's maybe a little bit of like Earth imaging, right? It probably makes up like, I don't know, 5-10% of the market. And I think 50% are like launch vehicles and telecommunications. And then you have like a sprinkling of like DoD stuff, and you don't really know how much money they spent on it, or at least, but it's probably like 10-15%, if I remember correctly. And that's kind of bespoke old space stuff. What I think is going to start happening is we're going to switch entirely to doing internet from satellite, so direct to phone, which means that the telecommunications, essentially satellites, are going to expand. I think there's just the market's going to grow the fastest there, and then you're going to get like layering kind of technologies and markets in space. You're going to get like servicing satellites, right? And by the way, it's I got to stop myself. I can't talk about this, but servicing satellites might become an increasing part of the market. There's a lot of plans to go to the moon and kind of establish a base there. I think more kind of traditional vehicle type objects are going to start landing on the moon. If I remember correctly, there's a company that landed a $300 million contract to mine lithium or helium-3 on the moon for like quantum compute here on Earth, right? Helium-3 happens to be the easiest place to get it is on the moon surface. You have folks like Astroforge who are like, okay, look, we can obsolete the entire mining industry, or at least the rare earth metals and kind of high value metals, by sending probes out to asteroids. And if they're successful, that's going to be a money-making machine, but it's going to be like 10 years out to 20 years out. So the cost has dropped low enough to launch things into space and to actually build things for space that everyone's like out there experimenting. It's clear that right now telecom and like direct to cell phone and direct to house internet is a big thing, and it's going to keep growing. But I think right now it's a lot of people are in experimentation mode, trying to figure out other ways that you can bring a lot of value from activities in space. That was kind of long-winded, but I hope that answers the question.
Okay. Well, I guess let's start wrapping up. I would like to thank everybody for the questions and for being with us. We will publish this video later on YouTube and perhaps some other platforms. We will send out any relevant material, links, whatever comes with the webinar. And so, Danny, thank you very, very much.
Yeah, Gregory, thank you very much, and it's been a pleasure to share some of this information. I think it's important to kind of, how do you say, bring a more entrepreneurial spirit to space. I think old space has been very closed up. Nobody wants to talk about anything. Everyone's kind of secretive. And new space is much more commercial. It's much more available. It's much more open to engineers coming in from all sorts of different disciplines and contributing to it. And I think it's not as how do you say, the barrier to entry isn't as big as it seems. When I first approached space, it was a whole wall of like gated gardens and terminology that's bespoke, and it's not that bad. And there's more and more information coming out, and I'd encourage you guys to check out Roid Rage. It's the podcast that Astroforge hosts on Spotify and YouTube and stuff, and they have a ton of very interesting information about what it takes to actually build a satellite. Everything from link budgets and RF antennas to power converters and avionics and solar panels and vibe and everything. So this information is becoming much more available, more so than the last space race. Let's put it that way.
Well, this is awesome, and thank you very much. It was fascinating. I'm sure we're gonna talk again in I don't know, we will schedule another episode with you. Thank you very much.
Totally. Looking forward to